Okay, yeah, today we're going to talk about blockchains, distributed apps in the Ethereum network. So, yeah, what we're going to talk here today, the agenda going to be first, Vitor will talk about Bitcoin and how we can implement some kind of distributed cash and how, a little bit about blockchain. Then we're going to look at Ethereum and how Ethereum is just a generalization of Bitcoin, or in the other way, how Bitcoin is a specialization of Ethereum. And then we're going to look about at the Ethereum virtual machine, so how Ethereum handles to run code. And then we're going to look about on Solidity, because Solidity is a language that compiles to Ethereum virtual machine bytecode. And then in the end, we're going to take a look about some new thing that probably you've never seen anywhere, because Vitor is working on the Ethereum Foundation, and he's working on a new browser for distributed apps. That's Mislight. It's like a new concept for distributed apps, because yeah, you're gonna see. It's gonna be funny. To make this talk possible, I need to thank Thiago, that is not here, but he helped us a lot in the contracts and stuff. And also me and Victor are going to present you a little bit of blockchain today. We work at Stone and we are hiring, so if anyone here wants to work with blockchain, with Bitcoin, Ethereum, want to do something funny, we're hiring, so talk to me after the talk or send me an email. And okay, what we're doing at Stone, just a brief thing that we're doing there. We are doing a Bitcoin payment system for our clients. We have like a lot of 70,000 clients, and we're doing something for they to accept Bitcoin. We are also doing a exchange, a crypto exchange, to exchange from Bitcoin and reals today, but probably more currency tomorrow. We are also working on a real-backed ERC20 token, so to allow people to use real in the blockchain to transact and create smart contracts with that. And we're doing Mislight. Victor is doing that. Okay, so first let's talk about Bitcoin. Just a second, because we have another presentation.
Você vai passar? Deixa eu passo. Okay, thanks. So before anything, I'd like to ask sorry. My English is not the best thing in the world, so if anything I say is not clear, please let me know so I can speak it again. Before I get into the Ethereum topic, I will make a brief introduction to decentralized systems and currencies. I will not cover the why we would like to have decentralized money or things, so I will just try to explain briefly how the technology behind everything works. So, okay, implementing centralized money, a centralized currency is something that's not very hard. Like you have a service like Amazon, and you get a database like MySQL, 5 lines of code, you upload the code and it's done. It's something that's really simple to do. Making money on the internet right now in a centralized way, it's not very hard. The decentralized case looks like it should be trivial too. Like if decentralized is simple, then it should be true. But we are like 3 decades trying to do it, and just a few years ago, we finally made it something that works. So the jump between centralized and decentralized systems, even for trivial centralized systems, is not very simple. So let's try to implement a decentralized currency. The first attempt. Everyone has a copy of the database. This is obviously necessary because, like, if there is no central party to hold the data, someone has to hold it. There is data on the system. So who holds it? The most obvious answer is everyone that participates on the system holds the data. Everyone starts with the same amount of money, and to make a transaction, to send money to someone, you broadcast a document, like there are 4 participants and someone participant Alice, Enzo, Luana, and Pedro. So say that Alice wants to send some money to Enzo. She just shows to everyone, I want to send money to Enzo, and everyone refreshes its database to reflect that transaction. So this is, for example, a transaction from Alice to Luana, value 10, sorry. So Alice spreads that through the network, and everyone refresh its database, his database. So that works. Obviously not. Suppose that, for example, Luana makes that document saying that Alice sent a lot of money to her and spreads to everyone. Obviously, everyone will receive that document and update its database. So that can't work. You can make transactions for someone else. So the second attempt, we will introduce authentication. Now everyone has a database of balance and also a database of passwords. And to send a transaction, you add the password of someone on the transaction. So that obviously helps, because now only Alice knows her password, so someone else can't make a transaction for her. And that works. Obviously not. Actually, the password is on everyone's database, so you can just look it and know the password of someone else and send a transaction in his behalf. So the third attempt is to introduce crypto authentication. Instead of databases storing passwords, they store public keys, and transactions include signatures, not passwords. Signatures are just basically a small document that says only the person that knows his password can generate this piece of data, and everyone can verify that this is true without revealing the password of that person. So that kind of solves the problem of authentication. That's why we have cryptocurrency. The crypto comes from the crypto signatures that allows someone to say something to everyone else without revealing his password. So that's how a transaction looks right now. We have transaction from Alice to Luana, value 10 something, and a signature. So now with that document, everyone can see, look at that, and run an algorithm and convincing themselves that only Alice could have made that string SIG and broadcasted it. So this document certainly was made by Alice, not Luana, not everyone else. So that works? No. We are making progress, but there is still one problem with his double spending. Suppose that, for example, Luana gets that document saying that Alice sent 10 something to Luana, and Pedro gets that other document saying that Alice sent 10 something to Pedro. And suppose that Alice has just 100, something. So what's the problem here? Two different persons received a valid document from Alice claiming that she wants to send 100 something to that person, but Alice has just 100. So the problem is, what of those two transactions come first? Like, who decides that? There is no central party, so both Luana and Pedro, they both want the money, and who has the money? Who says who has the money? Alice has vanished, and there is no central party to say, no, this is the right transaction and the other one is not. So this is a problem, double spending. So to solve that problem, we introduce a sorter. A sorter is like someone else. You can imagine just anyone in the world that you get the transaction that everyone sends and pick a order of those transactions. So the sorter can't send money to someone else, can't send money in behalf of someone else, can't make verifications on the system. The sorter just has one role, which is saying, this transaction comes first, this transaction comes after. So this is the database now. We have everyone with a copy of the balance, everyone with a copy of the public keys, and a list of transactions instead of the final state with is the balance of everyone. That works, kinda, but we just introduced a central actor, the sorter, and that guy can't be here because we are trying to implement something decentralized. So that kinda beats our assumption. So this attempt will now pick a random sorter every so minutes. So instead of just choosing someone to sort the transaction of everyone, we make a random pick of that person, and like every 10 minutes, that person decides the order of the transactions of the last 10 minutes. That's better because someone can't make an ordering for too long and have a central control of the order of the transactions. But if you do the randomization by IP, for example, it's easy to generate a lot of fake IPs, so that does not really work because someone can just like make a lot of IPs and be sorted all the time and become like a centralizer and order all the transactions himself. So the last attempt, instead of sorting someone to order the transactions by IPs, we do it by CPU power. The database now includes a proof of work field. The proof of work is basically a small little string that's very hard to make. And since that string is very hard to make, we know that someone must have spent a lot of CPU power to make it. And with that kind of proof, we can like randomize the orders in a way that now finally works because you can't duplicate CPU power. So why I'm saying all of this? I'm just trying to make the point that many people don't get this very well. They think that miners have the power to control the system, to change the balance of everyone. No, the sorters, the miners, they just pick the orders of the transactions and they group them in blocks. That's why we call it a blockchain. And the only reason we use proof of work is to choose someone to make the order of the last 10 transactions in a way that is decentralized, because CPU power is in a way already decentralized. You can't duplicate it. So that's all that mining is. There is not anything very mysterious about it. It's just a way to choose someone to order the transactions of our decentralized system. So does that actually work? Not really. Bitcoin is a currency that works. It is basically what I just said, proof of work plus cryptographic signatures. But Bitcoin still has some problems. We have a decentralized currency, but we have a lot of centralized service around that decentralized currency. And for example, MTGOX is an exchange that was centralized, so it was hacked. It did not gain the benefits of Bitcoin. Silk Road was another service that was also hacked. So, like, you have a decentralized coin, but centralized service. And then we need to raise another question. How do we implement decentralized services? How do we implement a decentralized computer? And that's what Amorim is going to cover right now.
Okay, yeah, so that's how Bitcoin works a little bit. Yeah, this is already done. Okay, so just taking a look again at blockchain. So the idea is that we have, instead of storing the end state, like the balances, we store all the transactions in the blockchain. But the point is, okay, how do we know how much money someone have? So have you ever heard about event sourcing? So yeah, event sourcing is you can derive a final state by looking at all the events that happened. So for example, we can start like with a empty state. So generate is a transaction that adds money to someone. So starting with just a first transaction, we can have like the first balance table. So only Satoshi had 10 something. And then adding more transactions updates the balance because we know, okay, this person earned more money, this person transferred money to someone, and we can derive the final state by iteratively applying the transactions to the state. Okay, if you look at Ethereum's paper, they say that this is a system that can be said to be a very specialized version of a cryptographically secure transaction-based state machine. Okay, so the question is, what is a transaction-based state machine? So if you know a state machine, something that receives some signals and change the state. But transaction-based machine, instead of receiving a signal, receives a transaction that is basically something related to the signal. So you know we have something like a transaction. So what a transaction is like create money, send money for someone to someone, and from there we can derive a state. In case of Bitcoin, can be something like user X has balance Y. In general, formally, we can say that any state I+1. The new state can be found by applying a state transition function using the previous state and the new transaction. In general, if you want to know any state at any given point, for example, the current state, if you know a little bit about functional programming, it's just like a reduce over all transactions, applying the state, starting the first state. This is wrong, sorry, and applying the state transition function. Okay, so that's basically how Bitcoin works and how Ethereum works. They all work in that event sourcing way. And okay, so let's talk about Ethereum, finally. So yeah, Ethereum is a project that which attempts to build the generalized technology on which all transaction-based state machines may be built. So what that means? That means that we can build Bitcoin over Ethereum. We can build any transactions-based state machine using the Ethereum network and the Ethereum virtual machine and stuff. Okay, about Ethereum, I'm going to give you some info about Ethereum right now. So the state, instead of being just mapping between addresses are like user accounts. Between addresses and balances, we have that called account state. That's in Bitcoin, it would be like just the balance, but here's something more complex. We have more information there. Accounts can have code, and that's called the contract accounts. That's why smart contracts. Smart contracts are like a special account that can have some code. And that code is run when that account receives a message. So if you have like a contract account and you send a message to that, then it's going to run some code that have in there. And we also have some in the network some form of value that is used for incentive for the sorter, the order for the miners. Because the miners have to run some code, they're going to waste some CPU time, so they need some reward. And that's the Ether. And that's also what you use to pay for the computational usage. And we also have transactions of two types. In Bitcoin, we have two types of transactions. The one that create monies, that the miners normally say, oh, create money for me, of course. And we also have the transaction that transfer money from point A to point B. In Ethereum, we have two types of transactions. The first one is message calls. So I can create a transaction that says, send a message to that address. Whether that is a contract or a normal person, that doesn't matter. I mean, that's not the point about. We can think they as the same thing. And we also have contract creation. Basically, you send a message to an empty address, and it will send the code to create that contract. The state is, as I said, the map between addresses and account state, and that's important. What do we have in the account state? We have 4 fields. Basically, we have something more, but in general, we have something, 4 things. First thing is announce. That is the number of transactions sent by this account. That is used to kind of synchronize the account state between all the nodes, and we use that on the cryptographic hash, so we can say kind of, okay, this is a valid transaction that comes after or before that transaction from the same account. And we also have the balance. The balance is basically the amount of Ether is stored in way, which 10 to minus 18 Ether. It's an integer. And we also have storage that is basically a persistent memory for all the accounts. And that's something that we need when we create a computer. And we also have some code that can be run when it receives a message, and it can be empty for normal accounts. Okay, so how we run code? I told you that you can send a message to that address, and the code will run magically. So how it works? You create a message sending to that account containing some payload. Imagine that you're using some kind of remote procedure call. You send a message, say, oh, call that function with that parameter. I mean, some payload in general. And then the state transition function that I told you, what it does is it checks if that code exists. If the code exists, it runs the code in the Ethereum virtual machine. Okay, what is the Ethereum virtual machine? Ethereum virtual machine is kind of a virtual machine, but instead of using the regular register-based implementation of RISC, CISC, processor, it is a stake-based architecture. So instead of writing to registers and then calling some opcodes for using register A and B, do something on the ALU and the CPU, you basically just push things to the stack, and operations do something with that. So Ethereum virtual machine is a stack-based machine. What that means is that you push values to the stack, as I said, and operations can consume that values from the stack and also add more value. So if you add like 2 and 3 to the stack, when you say, okay, run this opcode add, what you're gonna do is gonna take the 2 and 3 and take that from the stack and put 5 on the stack. And also, each kind of operation has some gas costs. Gas is not exactly one-to-one to Ethereum, to Ether, but it's kind of a relative value that say, okay, how much computational power that operation costs. And that is used because when you send a transaction, you can say, okay, the gas price is X Ether. Yeah. Okay, and we have like 2 types of states. The first state is the machine state. Like in your computer, like your registers and your DRAM memory, if you turn off the computer, it's done. It's not permanent. And that's the stack and the memory. The stack is like the registers in the regular computer, and the memory is the memory. And we also have an account state. That's something that's persistent, like a hard drive or SSD or something like that. And then we have a lot of operations, like if you take the CISC documentation, the Intel architecture, and see all the opcodes we can program in assembly and have like a lot of opcodes. The one that is special here is that we have some operations that take information from the environment. That's something important. You can take like, what is the call price? Who called that message? You can say, okay, in which block I am? What is the balance of the account that's running that code right now? We also have things to store and load from memory, from storage. And yeah, the basic of control flow. So we have like a Turing complete thing. It's basically like Redux. If you think about that, the idea of account state, if you ever programmed in Redux, you have the store, right? And basically you have some initialization function, you have some actions that you can operate on that, and you have that transition function. So you receive a state and a message, and you change the state based on the message. So yeah, similar to the way we do in Redux. So this is like something that you can buy, put money on there, and then transfer to someone else. Yeah, but this doesn't work. This is just an example to compare to. I mean, maybe that works in Redux, but it doesn't run on the Ethereum virtual machine, not yet. Actually, that's something behind the curtains. We have something like assembly. Like if you program for your CPU in assembly, you have like a assembly code. That's exactly assembled to bytecode. So it's even harder to read than that. But that's hard to write, right? You have to think about how to manage the stack, how to push things, I mean, it's just a mess. You can do that. It's feasible for small contracts maybe, but that's why you have Solidity. So Solidity is a language that compiles to the Ethereum virtual machine. It's similar to, let's say, C. You compile to your processor bytecode. And Solidity has some features. For example, we define contracts with just a fancy name for objects in the Solidity way of thinking. So just an object. So we have like internal states and message to that, and so on. Sending message is to the contracts. You invoke public message. If you take like the Alan Kay definition of object-oriented languages, it's just message passing, right? The way it used, because the Ethereum virtual machine doesn't have any idea about methods. It's just like run that code. And the way Solidity does is that it creates something called ABIs to have like an ID for each function signature, and then you send that. I mean, I think we're going to see that more in the next talk. And it's typed, so we have like some primitive types like integers, bytes, bool, and we have some arrays and mappings to collection built-in types. So we have like the arrays is array and mappings like a dictionary, right? And we can also define some structures. So let's implement yeah, this looks like a scam, but let's implement a token here. The idea of pyramid token is that it's something that starts with a fixed price. Every time you buy, the price increases, and when you sell for the last price sold. So if I buy, so if I am the first buyer, I buy for 1, and then 10 other person buys that, so the price is going to be now 12, and the last price will be 11. If I sell, I sell for 11, so I earn 10 something. And we also want to be able to enumerate all the accounts and tokens just to create like a best user interface, because you cannot like go through all the address space, because that's like 32 bytes, so you're not gonna do that. So, okay, so we start defining so yeah, now we're into code, sorry about that. So the contract is, I call that pyramid. And first we define some struct, like the user-defined struct that I told you. Basically, it's just account, it's just an address, and amount of tokens that person bought. And we also define some token counter. I mean, just like how many tokens have I minted, because that is used to calculate the price, right? We also have yeah, the increment by token, that's just something that I put here so we can create like a different version of the contract with 0.1, 0.001 or something like that. And then we have the accounts, and we have a map between address and ID. That's just the index of the account. So we can, okay, here's the address, what is the balance? And the arrays, so we can enumerate all the address, right? And the constructor just set the increment by token. And then we can create our buy function, okay? So the buy function first checks if the value, so we have like that environment opcodes that I told you, so we can infer something from the environment, like the message. So we can look at, okay, what is the value that has sent in that message? So we can, there's something that's built in on the Ethereum, you can send value through message. That value is something that changes the balance on the account state. So we can say, okay, how much money that person sent me? It's bigger than the price that I'm selling right now. If yes, I continue. If no, I return. And then I just get the ID, and I update the amount of tokens, and I update the amount of tokens total. I mean, I could like derive that, but that would cost like a lot of gas. So this kind of optimization to save the tokens for account and tokens for everyone. Pretty simple, right? I mean, and the best thing is that different from writing like a distributed thing on your own, you don't have to worry about concurrence, because actually it doesn't run concurrently. It's distributed, but it's not concurrent. So the miner runs that one by one. It's like serializable, right? If you think about database transactions. And we also have the sell function. Basically, it sees if the person has an account and see if the person has tokens to sell. And if it has, it's just sell by the last price sold. So it removes the token, removes the total token, and send the money to the person. Just a side note, it's important to send the money in the last thing you do, because there's some attacks like reentrance attack. I mean, let's not get into that right now. And it would just define some getters. This is just for the user interface, if you think about it. And also the get price is important here. Is say, okay, how I calculate the price for that token in a moment. And this is just something that I used there. It's basically just a function to get or create an account. So if the user doesn't have an account when buying, I just create an account and push to the account array. Okay, show me working. I'm talking sheep. Okay, it's running. Okay, so this is the contract. I'm using the remix. I recorded a video, so I don't have any not working things. So I'm using remix so I can deploy the contract. Here I'm deploying to JavaScript VM. So not running on the real network. So I can see the get price is, that's like 0.001 Ether. And then I can send the value 0.001 and buy. So when I do that, I can see that I have a new account created, the price increased, and the balance in that contract has increased, and the account 1 has 1 token. I can buy more things. Okay, so now I bought a little bit more, and now I'm trying to buy for the same price that I bought. I didn't work it, now work it, and then I will change account. So that account bought 2 tokens. I'm creating an account and I'm gonna buy like a lot of tokens, like 9 tokens. So 003, 004, 00 something, and what that's gonna do is gonna increase the price. So when I sell on the first account, I would have like won some money. Have some profit. Yeah, so by a lot. And now, if I see the first account has 2 tokens, the second account has 6 tokens, so I'm going to switch to the first account. This is just the IDE that you can use to try out your code. And now I sell the first one, I have only 1 token. I sell again, I have 0 tokens. And if I check my balance over there, now I have more than 100 tokens, 100 Ether than what I started with. Yeah. So now we're going to show the new thing, I mean, the mist. So Victor is going to present you. Okay, that's kind of hard to write code on that, right? You have to think about a lot of things, have to send the message. I mean, it's not user-friendly, so we want to create an interface. So what Victor is going to show you is something that he's developing for the Ethereum Foundation. If you want to do that right now, the next talk is going to talk about creating interfaces right now. So, yeah, just a second. Quer mostrar o vídeo?
A gente tem 14 minutos? Ou são 4? So, one of the coolest things about Ethereum, I mean, all those things that we said until now are kind of nerdy and tashy, but one of the coolest things about Ethereum is if you think about it, in the same way that Bitcoin was the first currency that was decentralized, like a currency that no one can destroy, no one can touch, no one can hack. That was what Bitcoin was for humanity. Now Ethereum is a step further. Ethereum is the first truly decentralized computer in the world. So think about it for a while and think how many cool things we can do with that. Think about it. You can like make an application, make a game, you can write an exchange, you can write a social network and put that thing on the Ethereum computer. And then it's there forever. Nothing in the world can make your application go offline. A meteor can fall in someone's computer, but it does not matter because as long as someone is running an Ethereum node in some random country in the world, your application will be online. That's the problem that Ethereum solves. So in my opinion, that's something very cool. Bitcoin, for example, can be seen as a special case of Ethereum. And this is something new. We don't know very well what kind of things this will give us, but we kind of have a feeling that this is something that will change the world in some ways. So one of the problems of Ethereum is a very new project, and as Amorim said, it is still very hard to use it. There's a lot of code, there's a lot of hashes and public keys and passwords and things like that that usual people, normal people in the streets don't just get. It's just not friendly to common people. So we kind of feel that in the same way that the computer in the 90s was in a state that all we had was the command line and the DOS and things like that, that was really hard for normal people. We think that Ethereum is on that state right now. And we think that the next step to make Ethereum actually go to the mainstream, make Ethereum actually grow to its full potential is to start exploring ways to make interaction with Ethereum more friendly than like what we just showed right now. So one of the projects that we are building right now on the Ethereum Foundation is called Mist. It has 2 versions. One is deployed right now. If you have heard about Ethereum, you probably know that there is a Mist project that you can download right now. But it was like a first step, and it's a browser that allows you to interact with Ethereum applications. Think Ethereum as a decentralized backend. So Mist is a browser like a front end that allows you to, with visual interface, interact with Ethereum. The problem with Mist, as it is right now, is that despite Ethereum itself being a decentralized computer, a decentralized backend, the front end, as we do it right now, is still centralized. So for example, if you see any application built on Ethereum right now, Aragon and ENS and many others, most of them have a normal computer, a normal server that serves a front-end interface to interact with the Ethereum network. So for example, if someone hacks the front end and puts something to steal your keys there, it will be a problem because it's not unhackable anymore. So we also have to think about it. We also have to think about how to make the front end decentralized too. And that's what Miss Light is the next step to Miss is trying to solve. Miss Light is a browser that's fully decentralized. And when I say it, I really mean it. When you download Miss Light, you get it from the decentralized hardware. And what does that mean? It's not on GitHub like Miss, it's not on the Ethereum Foundation server, it's not on any particular person's computer. It's in a decentralized hard drive that is running on the computer of many persons in the world. So the browser itself, the download of the browser is on IPFS, so nothing can take it off. Not a meteor, not a catastrophe. Beyond that, every single application that runs inside the browser is running in a programming language made specifically for this purpose that also is decentralized and also can't be taken away. So we have a small example to show right now. It's paused, I hope you can see it, but don't yet, just a second. There we have a MacBook with the browser open. You can see that I'm using Chrome and the browser is running inside Chrome. That's not a problem because the browser can run another browser, but obviously you would download a binary, not run it inside Chrome like I'm doing right now. So just ignore Chrome for now. But I think Chrome is nice. So you can see that, for example, on the URL bar, you see gateway.epfs.ap/some hash. What does that mean? That means that this interface is being downloaded from EPFS, which is a decentralized hardware, just like I explained. So welcome to Moon. This is the browser. You can see the URL bar in the browser is not an IP, it's a hash, and that's important because that hash is how you get some info from that decentralized hard disk. So you have buy, sell, and I think, mais 2 minutos. You have buy, sell, and this is an application running on that browser. And now we will show, for example, how you can get that application. It's to buy and sell the pyramid tokens that we just programmed. You can see it's a simple visual interface. It's kind of ugly. It's the first thing we did, like we did it yesterday. It's something very new. But what we are trying to show right now is how you can get that application, change it, and it will be hosted on the IPFS, and instantly, in the same moment, without needing a server, in a few seconds, we can get that same application changed to run in another device, and in any other device in the world, and it will be there forever. So that's the point I'm trying to make, please. So I'm editing that application on the browser. So I'm changing the colors, I'm changing the font. This is an editor that is inside the browser. And I would like to ask you to pay attention to the hash, which is the URL, because as soon as I click there, the hash changes. And when that hash changes, this is already on the decentralized hardware. And anyone in the world can now use that hash to get that new version of that application with a black background. So this is on iPhone, and I'll get that hash on my iPhone, that string right there. So my iPhone is kind of slow, and it's not edited, sorry. So I select the hash, get back to the browser on the iPhone. I will put that URL, that hash, on the URL bar, and you can see that on my iPhone I can access the application that I just built on the other computer. And that application is there forever. Nothing can hack it, nothing can steal your passwords, nothing can make it go off. So that's what we are trying to do with Miss Light.
Yeah, thank you. I think we're running out of time, so if anyone have any question, sorry, that was like a rush between through a lot of things. If you want to hear more about Ethereum, it's going to have like another presentation right now about creating interfaces with JavaScript. Yeah, so any questions? We have time for questions? I don't think. Yeah, okay. Yeah, thank you.